Good morning, everybody. How are we doing today? Yeah, we're all right? You won't be in when I tell you that the time change happens this coming weekend. It feels like it already did, right? Yeah. But we lose an hour of sleep Saturday to Sunday, so just watch out for that. We have something very, very important to talk about. Something that affects you directly and something that needs to happen. Okay? Like, go see it. Like, seriously. Excellent movie. The first one was fantastic. The second one, just as good. I'm going to go out on a limb here, okay? This is my nerd cred on the line. This is the greatest science fiction epic since 2001: A Space Odyssey. To be clear, I don't consider Star Wars a space epic. Okay? Right? Star Wars is a series of movies that I love, right? But it's not a space opera or a space epic the way that 2001 is, Interstellar is. This is just, it's amazing. In an age when people complain, it moves too slow, I'm like, oh, give me slow. Like, take time to enjoy the cinematics and all that kind of stuff. So, compared to the first one, it was great. It was fantastic. I mean, we don't have time to go into all of my little niggly bits about where they messed up from the book and all that kind of stuff. But that all, push that aside, these are a fantastic set of movies, right? And true to the spirit of the books. Can I recommend the books to you? Dune, Frank Herbert, the author of Dune, he doesn't write well. Like, it's a wonderful story. He's an excellent world builder, but, like, it's dense. Like, it takes work to read it. So is it worth it in the end? Yes. Is it something that I can wholeheartedly recommend? Nah, go watch the movies. Right? Okay. So that's where it is. Anyway, I got to see that this weekend. It was fantastic. All right, on to things of actual importance. So we've done chapter 7 and 8 last week. We're doing chapter 9 this week. There's only 3 chapters on this upcoming exam. So when does that mean the exam is? It's next week, right? Okay. So we get chapter 9 today and Thursday, and then we review next Tuesday for taking the exam on Thursday. That just feels fast, and it is. Okay. This is, I think, the shortest unit we have in the semester. So I just hang on for the ride. Right? Hang on for the ride. All right. I do need a volunteer. Somebody up here that can help me demonstrate something. I promise you won't get hurt. Thomas, you willing? Thank you. Okay. Well, you might get hurt mentally. Okay. Will you please spin the wheel? Okay. Did everybody notice where he grabbed the wheel and how he pulled? Do it again. Oh, okay. So which way did you pull? Down. Down. Right? Okay. Grabbing more or less right here, right? To get this thing to spin. What Thomas did is he applied a torque to the wheel to cause it to spin. Now I want you to notice something. Okay, so Thomas, you grabbed it here and you pulled down to get it to spin, right? What I want you to do is like with the flat of your hand, okay, I want you to push up. And what I want you to do is I want you to push directly towards the center of this wheel and try to get it to spin. Right? Okay, so were you playing? No. You weren't playing. It was pushing hard, right? Okay, right? But notice there was no rotation of the wheel, right? Plenty of force, but no torque. Think about the difference between the two things that Thomas did. Okay, Thomas, come over here. I'm pretty sure I set this up correctly. Please stand in a location where everybody can see what you're doing. Please open the door. Okay, wait. Why did you grab it right there?
Thank you.
Because that's where it's
Because the handle is right there, right? Okay? You open the door by grabbing, go ahead, open the door again. Wow, you got skills. Okay, so come over here. Stand right here. Okay? Ignore the other chemistry teachers. Okay, now, with one finger, I'm just going to kind of put my foot here and hold it. With one finger, I want you to open the door. Everybody, ooh, okay. Everybody see where he pushed? Okay, now don't hurt yourself, please, right? I want you to try to do the same thing, but like right here, just with one finger. Right, okay? That didn't work, did it? Nope. Okay, right? Can you go right here with your whole hand and open the door? Okay, all right. But how much effort did that take compared to staying here? Right? Yeah. Okay. What's everybody give Thomas a hand? Okay. What is going on? Right? Why is it that out here only a little bit of force is necessary to get the door to rotate? Right? But over here it takes a lot, okay, to get the foot. What's different about these two places?
Leverage.
Yeah, but specifically.
Radius.
Yeah, there's like a distance here, right? I've got an axis of rotation around the hinges, right? And I'm getting the door to rotate, and it seems like the further out we get, the easier it is to get the door to rotate, right? I can apply less force at a bigger distance to get the same amount of torque. Over here, to get the same amount of torque, I have to push harder because my distance is smaller to my axis of rotation. And, like a bicycle wheel, if I try to open or close the door by pushing directly into the hinge, I don't get any kind of rotation whatsoever. That's the way I would do it. Yeah, right?
Keep walking.
So, just ignore the chemistry, right? So, what's torque? Is force involved? Yes, there's definitely pushing, isn't there? Pushing, pulling, whatever, right? But importantly, there's pushing or pulling that takes place at a certain distance from a point of rotation. So, I have a lot of questions here, okay? First of all, why is the door round? I mean, hobbits are famous for building their things right in hobbit holes and all that kind of stuff. But why round doors are so hard? And do you notice where they put the doorknob? Right? I mean, to a designer and an artist, it's pleasing to put the door. Why is the doorknob over here?
Where pushing and pulling is easiest.
Aha! It's where we can apply the greatest amount of torque, isn't it? If we put the doorknob in the middle of the door, we have to apply more force to get the door to open. And we'd have to have like a big piece of metal, right? To go, stupid hobbits. I mean, they've got good ideas when it comes to food, right? First and second breakfast, I can get behind that, right? But when it comes to their architecture, oh boy, do they need help, okay? So anyway, torque. Remember we've been going Greek, right? So instead of a T, we are going to use the Greek letter tau. I usually write it like that. Technically, like tau is either something like that, or it's got a little squiggly. Sometimes it's just a little kind of a squiggly like that, okay? But I usually it's almost like my T's, right? Like I'm gonna go for a T, right? To make a T or maybe a T like that. But instead, it just doesn't poke up above the crossbar, right? That's the Greek letter tau. It's our symbol for torque.
Is that capital or lowercase?
It's lowercase tau. And not that I really understand or know the difference in Greek. Your book writes this as F times L, where L is some sort of lever arm. I'm going to write this is a little bit of a Mr. Baloghism, but I've seen other physicists do this. And it's a notation I actually really like, okay? I'm going to write a distance, r, a radius, like a distance from an axis of rotation. And then I'm going to do an upside down what looks like an upside down T, and then I'm gonna put an F right there. So that upside down, almost T looking symbol means perpendicular to. So the reason I like writing it like this, as opposed to the way your book writes it, and it's not wrong, okay? Your book says F times L, okay? Is that I need to be reminded of something, right? Okay? I'm applying a force to this thing that I want to cause to rotate, right? But critically, the force that I'm applying, which is directed outwards from the door handle, right? As I pull on it, that force needs to be perpendicular to my distance from the hinge. My distance from the hinge goes from the hinge through the door all the way to this point. And then perpendicular to it, I can apply the torque. What happens if my force is not perpendicular to that? No torque takes place, right? So I choose to write it as R perpendicular to F. That's what that symbology means, because personally I need the reminder, right? I need to be triggered into, oh yeah, okay, I need perpendicular things, right? Because what happens if I pull not perpendicular? So if I'm trying to do this, where it's like I'm pushing or I'm pulling and I'm exactly parallel to that distance, nothing's going to happen, right? But what happens if I pull like this way? Am I able to apply some torque? Yeah, but it's only the perpendicular component that's helping there. The component that's parallel to this distance isn't doing a thing. So we're going to have to pull off components of stuff. If we've got any angles between our distances and our forces, we'll have to find components. So that's why I personally like to write it like this. I need the symbols to remind me of that relationship right there. The units here. What are the units? What are the units of force? It's a Newton, isn't it? Right? And then, what are the units of distance? It's a meter. Okay? Now, in case those of you that are mildly awake might notice, these are actually the same units as joules. Force times the distance. But it is a unique thing. Even though they share units, we keep torque in newtons times meters. Right? But a force times a distance technically could be work, and we'll get to work. We'll get to rotational work Thursday, right? But we're gonna keep this in Newton meters. Anybody that's ever worked on a piece of equipment and has worked with torque probably have measured that torque in foot-pounds of torque. Feet for the distance, pounds for the force. It's just the imperial systems version of it. Okay. All right. And no special name here when it comes to torque for a Newton times a meter. So let's talk equilibrium. Equilibrium is an easier place to start when it comes to talking about torque, because what we're segueing into here is how do we do forces in rotation. We've done kinematics in rotation, but now we're trying to do Newton's laws in rotation, okay? First law, third law, they still apply. Second law gets a little bit different, okay? We are going to apply a torque. Notice I pull down my distance from the center of the wheel to where I'm pulling. I pull down tangent, right? Perpendicular to that distance, to that radius. If I apply a torque, what does it cause to happen? Rotation, right? So torque are rotational forces. It's the idea of force, but in this whole sense of rotation that we've got going here. It causes alphas to happen, okay? But when it comes to static equilibrium, which we have talked about before, we talked about static equilibrium in the last unit. We are trying to achieve a situation where the sum, you add up all the forces on that bridge, And by golly, what do you want the answer to be? What must the acceleration of the Golden Gate Bridge be at all times? 0. Right? Because if it's not 0, the bridge's motion is changing somehow. And in a linear sense, if we add up all the forces and add them equal to 0, it means that we don't want it accelerating up or down, in or out, or right or left, right? We can go in all 3 dimensions if we needed to. So we want the acceleration of the Golden Gate Bridge to be 0. What do you think we want all of the torques to add up to? 0, right? Because we don't want the bridge to change its rotation. Right, okay? There is an entire career and branch of engineering that is dedicated to making sure both of those things are 0 at all times. And it's called civil engineering. Civil engineers, building bridges, building buildings, building roads, want to make sure that they're in static equilibrium. This is downtown Manhattan. And what can you tell me about every single building in this picture? The motion isn't changing. They're not speeding up, they're not slowing down, and they're not beginning to rotate. And so that means the sum of the forces and the sum of the torques all have to add up to 0. So let's do an example where we are going to take advantage of this concept and idea that if the acceleration, and when I say acceleration now, I mean linear acceleration, A, but now I also include alpha. I don't want there to be any A, I don't want there to be any alpha. This is a static equilibrium problem, okay? Where A equals 0 and alpha equals 0. Okay? All right. So we've got to visualize, and a picture is worth 1,000 words, and unfortunately I did not put 1,000 words on the screen. So to put a picture, okay? So this can be a little bit, it can be hard at first, right? But we've got this beam, okay? And we know that it's attached to a wall and a wire, and we're hanging a sign off the end of the beam. So what this is supposed to, so here's the wall, this is all solid. Here's the beam, and you're gonna see pictures similar to this, okay? The beam could be at an angle or something like that. I'm doing a horizontal beam for you at first here. And then there's this wire that's attached to the end of the beam. And then there's like a sign hanging off the end of the beam here, okay? Yes, no? No. No, definitely not. If you ever see me running for public office, something has gone horribly wrong. Like the aliens have arrived and they've taken over my body, shoot me now, right? Okay? Besides, you don't want me for president. Very first thing I do on my first day as president, executive order, sweats are now considered appropriate attire for every situation, right? Okay, right? Second, all SUVs are banned. I've got a long list, I could keep going, but yeah. No, you don't want me for president, so let's erase that. We'll just put a little object here because, all right. Another thing that's happening to you for the first time is that up till now in this class, it really hasn't mattered what the physical dimensions of an object are. I mean, it's been a tungsten cube or a penguin or whatever sliding down the hill, right? Or a car rolling down the hill. We never had to consider how big the car was or where the wheels were, any of that kind of stuff. Well, now it does matter. Torques depend on where these forces are applied. The lengths of things are going to matter now. And so, key thing in any static problem is to identify the one, again, we want to draw a free body diagram here, right? Free body means a singular object. Identify the thing in the problem to which all objects are attached. We've got a lot of objects in this problem. We got a wall, we got a wire, we got a beam, we got a sign, right? We got the earth, okay? There is only one object in this problem that is connecting every object. Do you think you can identify it? It's the beam. The earth's pulling on the beam, the sign's pulling on the beam, the wire's pulling on the beam, and the wall's pushing on the beam. The beam is like, the wire doesn't pull on the sign, does it? Okay? The wall doesn't interact with the sign, right? They're not touching each other. And so, kind of key to any statics problem is to look for the thing that connects all the things, right? You've got a lot of objects flying around. There's going to be a central member, sometimes is the technical word that we use to describe that thing, right? But here, it's going to be the beam. So we're going to draw a free body diagram of the beam, like all the forces that are acting on the beam. And one way to make sure that you can keep track of everything that's going on is start on one part of the beam and then pretend like you're, I don't know, like an ant or a bug or something, and you're going to walk all around the perimeter of the beam. And if you run into something, you're going to consider what forces are happening. So let's start at the wall over here. Okay, we're going to walk along the top of the beam, right? Okay, so we're at the wall. What do you know about when objects come into contact with each other? If they're pushing against each other, what exists? A normal force, right? Perpendicular to the surface of contact, right? So, I know that there's going to be some sort of normal force at the wall, okay? So there we go. I walk around, so I'm an ant, I'm walking around, I'm not running into anything until I get to the other end of the beam. And now kind of a whole bunch of stuff's going on, isn't there? So the wire, what sort of force do wires and ropes and strings and things exert? They exert tensions, right? And so this tension is going to be directed back along that wire. Okay, so I'm just going to draw it in there and label it. All right, is there anything else going on at the end of the beam? What do we got? The sign, right? Okay, so which way is the sign pushing or pulling on the beam? Down, right? It's got weight, doesn't it? Okay, so the sign is pulling down on the beam. It's going to pull down with its weight. Mass of the sign times MSG. I like MSG. I put MSG in a lot of stuff. You guys heard that MSG is bad? It's a lie. MSG is yummy. That's what they meant. The reason that you may have heard that MSG is a lie has to do with racism. Back in the 40s, like post-World War II era, Chinese immigrants, Asian immigrants were coming over and they were being very successful in their businesses and all those things because they work hard and do all these wonderful things that America espouses. Well, Americans were getting upset, and so they started a campaign where they said that this food additive that's used a lot in Asia called monosodium glutamate causes cancer, headaches, fill in the blank. It was a fear campaign, right? To the point where Chinese restaurants had to put up signs, and some of them still have these signs up saying, "We use no MSG." Okay? Total lie. MSG doesn't cover it. MSG is what makes like beef and turkey yummy, right? It's a flavor component that causes our taste receptors to go, ooh, meat, okay? And so, yeah, there are some, obviously, there are people out there who are sensitive to MSG. If you're sensitive to glutamates, right, then you might have a problem. But by and large, nobody is. And you want to make people like your cooking. Little bit of MSG in there, and they'll go, oh, this is the best fill in the blank ever. Don't put it on salad. Anyway, yeah. Always question why people tell you stuff. All right, so, where was I? Oh, racial tensions. No, MSG. Okay, we're done with the sign, we're going back. Do we run into anything else as we go back along the beam? There's one object we haven't considered yet. What? No, well, we kind of got the wall, right? We got that normal force right there. The Earth, right? Okay. This beam has mass, doesn't it? The beam has a mass of 20 kilograms, so the Earth is pulling on it. Now, tomorrow in lab, we are going to do a lab that deals with the center of mass. I'll teach you about what the center of mass is, and then we're going to do a lab on it. So it's going to be a little bit of lecture tomorrow, like first 20, 25 minutes is going to be lecture about center of mass. The Earth pulls on this beam at its center of mass. Where do you think that center of mass might be? At the center, okay? It says it doesn't really say if that's where it is, but that's where you assume it is if you're not told otherwise. So the beam, mass of the beam, m sub b times g, that would be the weight of the beam right there. So that one's kind of an easy one to forget, right? As you're walking around the perimeter or something, it might be the one you want to do first, right? Just to consider the weight of an object. Now, they could say in the problem, for example, kids get on a teeter-totter, and they say that, they'll say, ignore the mass of the teeter-totter. So there, you don't have to do anything about it, right? Like maybe the teeter-totter's so light compared to the kids, it doesn't matter. They'll also use that word that I can't say without thinking about it. It starts with an N and means it's not important. Negligible, that word, okay? Can't say negligible. So if they say to ignore the mass of the beam, teeter-totter, ladder, whatever, or that the mass is negligible, right? They're trying to communicate to you that you don't need to worry about that weight vector. All right. Okay, so we've kind of gone around, right? We've thought about every object that can be pushing or pulling on this thing. We've got kind of some new tools here, but some familiar ones, right? These questions that I kind of begged you to think about, right? What objects push pull? It was all coming towards this moment, okay? So now, okay, so it's not a complete free body diagram until we add what? There's something missing here. Coordinate system. I need a way to talk about what's positive, what's negative, okay? And you want to, since the accelerations are all zero, there's no rule of thumb that says point them in the direction of the acceleration. There is no acceleration. So, what do I pick? If it doesn't matter, can I just pick anything? Should I pick like a rotating one? Shaking heads up here. Why don't I want a rotating one? I've got a lot of forces that are already pointing vertically and horizontally, don't I? So in fact, there's only one of them that's not obeying, right? So I want to make sure to pick a coordinate system where I have the least number of components I have to figure out, right? Okay. So it looks to me like I can go with a standard up is positive, right is positive coordinate system. Because my weights are pointing in the negative y direction, my normal force is in the positive x, and the only one now that I've got to find a component for is tension. They do tell me that this angle right here is 35 degrees. And since now I know that that tension is not just x or just y, I better go find components of it. So let's see. The x component of that tension, which points to the left, sine or cosine? Cosine, why is it cosine? It's touching the angle. T cosine theta, and then I've got the one that points up right here. T sine theta, and we're done. Right? Components are no longer a problem. You got touching, not touching, and away we go. Okay. So, with those accelerations being zero, and knowing that Newton's second law in linear terms looks like this, and that we're setting this equal to zero, what we want to do is we want to add up all the forces in the x direction and all the forces in the y direction, they need to add up to 0. Well, we've been here before. We know how to do this. How many forces are there in the x or horizontal direction? There's 2, right? There's the normal force and t cosine theta. So normal force, positive or negative? It's positive. T cosine theta, positive or negative? Negative. Stop and check. Can you get to 0? Is it possible to get to 0 if you have one positive thing and one negative thing? Yes. If you had written at this point all positives, there'd be a problem. Right? We need to get to 0, so something has to be in the opposite direction. Okay. What about in the y direction? What forces do I have in the y direction? All right, we'll do 2 sine theta. We got an MVG and we got an MSG. Leave a little space in there. It's supposed to be a theta right there. Okay. T sine theta, positive or negative? Positive. MVG. Negative. MSG. Yummy. All right. So, can we get to 0 if we have one positive and 2 negatives? Yep, it's possible. So I'm feeling pretty confident about that. So that part right there shouldn't have felt new at all. That's old. Not trying to offend you. You may have forgotten. That's okay. Right? But we've been here before. Right? It's okay to forget. It's even better to remember. Right? So now we have a new thing that comes from the chapter, and that's Newton's second law in rotational terms. But I haven't showed you that yet. But we do know that, I'll show it to you right now. Don't panic, don't panic, don't panic, right? But there's a new thing for mass that we're going to talk about here in a second called moment of inertia, right? But we know that the acceleration, the angular acceleration has to be 0. So it doesn't matter what's over there on that side, right? We are, for the torques, going to say 0 equals, and now we're going to put in all the torques that we have in the problem. And this is the new part, okay? So focus on this. In order to be able to talk about torques, we need to have an axis of rotation. A point about which we define all of those torques. Is this object rotating at all? No. This is a theoretical point about which we can rotate things if we wanted to, okay? To figure out what the torques are. And there is a rule of thumb for you in choosing where to put your axis of rotation. You always want to put your axis of rotation at the location of the greatest number of unknown forces in your problem. That's, again, a Mr. Balogh rule of thumb that keeps us safe, makes the math easier, okay? There's a location on this beam where we have the greatest number of unknown forces. So what forces do we know? Do we know MVG? Did they give us a number for the mass of the beam? And we know what planet we're on. So that's a known thing. What about MSG? Do you know MSG? Yeah. Okay. What about the tension? Do we know the tension? No. What about the normal force? Do we know the normal force? No. So, I propose to you that there are 2 places that sort of jump right out at me as to where I want to put an axis. Again, this is an imaginary thing. Put an axis about which I can start talking about torques. And it would be either end of the beam. Because I have an unknown normal force over there, and I've got an unknown tension on the other side. What you're going to do is we're going to only write down one of those choices, but you're actually going to think about both. And I'm going to show you why. You want to choose both and do a quick check to make sure that we can get 0 torque. So let me demonstrate this. And this is the one I'm actually going to choose in the end, okay? But I'm going to put an axis right here. I usually put an X and then I draw an arrow and I label it because I've got to remember what I picked. okay? This one feels a little bit more natural to me in the sense that if we like cut that cable right there, won't the whole thing just sort of rotate down, right? I feel like it's attached to the wall somehow maybe, and if that cable snaps, it's just gonna kind of do that, right? So just, I don't know, it just feels better to me. But from this axis, we need to check to make sure that we can get zero torque. And so what you're going to do is you're going to take your pencil and you are going to hold your pencil like it is there in the picture. Notice how, everybody take your pencil, hold it horizontally and hold it down on the end where I've done the axis, right? Okay, MBG. Which way is it pulling on the beam? Down. So grab it in the center and pull down. Does your pencil rotate? Does MBG cause a torque? Yes, it does. Which way is it causing rotation? Clockwise. Clockwise, right? Causing rotation clockwise. Okay, what about MSG? What would you do for MSG? Grab the tip and pull which way? Down. Which way is it rotating? Also clockwise. Okay, we got two clockwise. That's not zero, right? But what about T sine theta? This one you either push or pull upwards, and which way is your pencil rotating now? The opposite direction, and that's the key right there, right? We had two that cause clockwise, but we got one that causes counterclockwise. Can we get zero? Yes, it's possible to get zero in that case, right? All right, let's do, what about T cosine theta? Does T cosine theta cause a torque? No, right? Like pushing in on the door towards the radius, right? T cosine theta doesn't cause any torque. What about the normal force? Double no. Not only is it parallel, it's also zero distance from the axis, right? So it can't exert any kind of torque. So it's just those three. Okay, so now we're going to grab the other end of the pencil, right? We're going to check the other end where there's, again, more unknowns there, right? Okay. And now, what do we got? We've got MBG. Does MBG cause a torque? Which way? Counterclockwise, right? What about N? No. What about MSG? No. Why does MSG cause no torque? It's zero distance from the axis, right? The axis is on that point, and you can't, remember, torque is distance perpendicular to force. If the distance is zero, what's your torque? Zero. How much torque does T sine theta cause? Zero. How much torque does T cosine theta cause? Zero. What's the only thing that's causing torque if we put the axis on this end? It's only the weight of the beam, MBG. And it's unbalanced. It's the only one that exists, which means we have made a mistake. Mr. Balogh, we're like 40 minutes into class and we've made a mistake already. Yeah, we missed something at the very beginning. Okay? So, knowing now that we've got an impossible situation where we've got just one torque, and one torque means we can't get an alpha of zero. It's like you have one force acting on something. What's its acceleration? Well, anything but zero, right? It's unbalanced. We need a balancing force somewhere. We've missed something. And where is the only other place? If our axis is on this end of the beam, and we've got the weight of the beam holding down, what's the only other place that can be applying a force? It's the wall. It's the only other point of contact, right? Which way does the force in the wall have to be pointing in order to counteract a counterclockwise torque? It has to do a clockwise torque, which means there has to be a force right there that can keep this in equilibrium. We can't invent forces. Forces must come from the interaction of two objects. So what are the objects here? The beam and the wall. Well, we've already got the normal force, Mr. Balogh. So what's this? Can you name the force that acts upward that is perpendicular to the normal force? How fun is this? Not fun at all, Mr. Balogh. It's static friction. It has to be there. If static friction weren't there, if I had a situation where like this thing was sticking out of the door like this or something, right? And I put a string right here, right? I have a normal force, but if this was frictionless, what would this do? It would just slide out, wouldn't it? Okay? This is why you want to say, okay, I'm going to put an axis on this end and I'm going to figure out, right, if I got balanced torque. And then you want to pick a different spot and see if you can do the same thing. It's going to uncover mistakes. Okay? So be sure to, even though I've only written down one axis and it's going to be the one I'm going to use, okay? You just want to do that quick conceptual check. And then you'll be not guaranteed, but 99% of the way to figuring out if you've missed something somewhere. Because it is easy to miss. There's a lot of stuff to keep track of. All right. So, with all that being said now, back to this axis. I can't really write down anything about torques unless I choose a positive, like a coordinate system for torques. So your choice is this. Positive is either clockwise or counterclockwise. You may choose. Which one do you want? Counterclockwise? That seems pretty normal and generic. It doesn't matter. All that matters is that you stay consistent with your choice. So counterclockwise is sort of the standard as we rotate around like a unit circle or something, right? That's the positive rotation direction. Okay. With all that in place, how do I write down these torques? Well, nothing's going on at the axis, okay? Neither the normal force nor the friction are applying a torque because they're at zero distance. Okay? I come out here, I already know MVG is causing a torque. So watch what I do here. I'm going to write tau. I'm going to leave space for a sign. I'm going to write tau, and then in subscript, I'm just going to do MVG. This is the torque from MVG. Notice I'm not worrying about how to write out a torque. I'm just identifying that it causes a torque. And then I'm going to write a torque from MSG. It causes a torque too. What's the other thing that causes torque that we already identified? T sine theta, wasn't it? So I'm just going to do torque from T sine theta. It's kind of ridiculous to write all that out, but I'm going to do it anyway. Okay. I've identified the three things. It could be more, it could be less, but it's certainly got to be two. Minimum of two, right? I've identified the things that cause torque. Now I'm going to do direction. What direction, positive or negative, is the torque from MVG? I grab my pencil, I pull down. Which way is MVG causing rotation? Clockwise. And what did we say about positive directions for rotation? Clockwise would be negative. So we put negative sign on it. Maybe. If I had not my eraser tool. There we go. Okay. All right, what about MSG? Grab your pencil, pull down on the end. Which way is it rotating? Clockwise, and clockwise is negative. And then T sine theta? Positive. Notice that I am going stepwise through this. I'm not trying to do directions and torques and everything simultaneously. I identified the three torques that I have. I went and did their directions. And now I'm actually going to write out what those torques are. Because torque, remember, is distance and force that are perpendicular to each other. So now if I want to write out the torque due to MBG, I need the distance to MBG. How far away is MBG from that axis? Half the length of the beam, isn't it? Do they tell me what the length of the beam is? No. Panic begins to set in. But we've kind of been here before. Sometimes when they don't tell us something, they're trying to tell us something. I'm just going to put in L over negative L over 2. Again, the negative sign comes from the direction we already did. And then what's the force? The torque due to the weight of the beam. What's the force? The weight of the beam. MBG. And then I pick up another minus sign from the line above. The torque due to MSG. What's the distance? How far away is MSG from the axis? The entire length of the beam. And what's the force? It's MSG. Are those things perpendicular to each other? Yeah. Right? Okay. What's the distance from the axis to t sine theta? Just the length of the beam. And what's the force? T sine theta. And that's all equal to 0. What just happened? A lot of stuff just happened. A lot of stuff that was old. So we did a straight up Newton's second law problem up here at the top in X and Y. That was straight out of chapter 4. And then there was a new thing with all of these torques. That's the part from chapter 9. Okay? Coming together in this static equilibrium problem. Where does it come from?
Yeah.
So like, what's its value or number or why is it in there?
Yeah, what?
The reason that it's in there is that torque has to be a distance times a force. It's got to be the distance that is perpendicular to where the force is acting. So I needed some way to describe what that was, right? If the beam was 2 meters long, right, I could have put in 1 meter times MBG minus 2 meters times MSG minus, plus 2 meters t sine theta. But I don't know. They didn't tell me what the length was, so I just stuck in a symbol for it. Now, since I don't know what the length of the beam is, and now I'm going to move into math problem solving mode, okay? I am hoping that that length cancels out somewhere. That's my hope, because I had to invent a symbol to keep track of it, and they didn't tell me what it was. And if I want to know the tension in the wire, okay, is there a way for me to solve for that tension? So my tension's here, but in order to get that, I need to know the normal force, and I don't know what the normal force is, right? Looks like, oh, I didn't go back and fix my y equation. What's wrong with my y equation? We added a force, didn't we? So we got to include that force. And now I've got to include that equation. Oh my goodness. So I can't really find t because I don't know this, which means I don't know this, which means I don't know that. So the x and y equations look like a trap. What's going down here with the torque equation? How many unknowns do I have in my torque equation? Well, I've got L. So all these L's, I don't know what they are. And T. What's my plan? mathematically? Go find a math major, make them do it. Oh. The L's disappear. Why did the L's disappear? I got 0 on one side, and I have L in every term. So if I divide the left side by L, what do I get? 0. And if I divide the right side by L, what do I get? I get L's in every denominator down here, right? And what happens to all those L's? They will cancel themselves out. Leaving me with negative MBG minus MSG plus T sine theta. And now, the only thing I don't know in that line is the tension. So I can solve this for tension, which I did somewhere. I got 855 newtons. Not showing you the math there, okay? Now that I know the tension, what can I find? Going back up to the X equation. Can find the normal force, right? And once I find the normal force, or since I already have the tension, I can go ahead and find the friction. I don't even need to know what the coefficient is. I can solve the Y equation for F. So I'm skipping over probably about half hour of math, right? But it's now possible. We've been able to unlock this thing a little bit.
Why does the 2 disappear?
It doesn't. Yeah, it's magic 2. It's the same 2 that some of you forget to write on your squared factors in your exams. Right? It's easy to forget factors of 2 and minus signs and all that kind of stuff. Thank you. That was a legitimate mistake. I wasn't even faking that one. See, I make mistakes too. But I've got, 51 awesome people telling me where my mistakes are. Teaching is a little bit like having to take an exam every day. Because all of you look at me like I know what I'm doing. Not really. All right, so we pretty much unlocked everything I can give you. Let's see, the normal force in this problem turns out to be 700 newtons. The, I didn't even write it down. That's 2 zeros, because I'm very sloppy. 700 newtons. Force exerted on the wall by the beam, that could be the normal force, it could be the friction, or it could be the combination thereof. It doesn't matter. What's important takeaway here is that you have a pattern for setting these things up. So let's just take a step back and like what happened here, right? Okay, first of all, you're going to do all of the forces like you did from chapter 4 and set it equal to 0. Okay. Second, you need to do some of the torques. And by this, you need to choose an axis, right? And then go through that 3-step process, right? 3 steps. You're going to write down the torques, you're going to do the signs, and then you're actually going to do the definition of those torques, okay? And you want to break it up and use a lot of these tricks and tips that I've told you, right? About getting your pencil out and seeing what's happening. Try to do it in a part of the library where people can't see you because you'll just look like you're crazy, right? That's what But those are the sort of the additional steps or processes that you need to go through in the strategizing part. We've got a visualization and a strategy, and then it develops this huge math mess. But could have expected that. It's Newton's second law. So you know it's just going to get real messy real fast. Let's get into some other parts of this, okay? That I'm hoping as we move forward and get into the blissful realm that is energy, okay, will help make a little bit of sense. But before we get there, I do need to talk about rotational mass. So far we've been defining angular things that are related to linear things. We did it with kinematics, where instead of V we had an omega, instead of A we had an alpha, and now instead of force we have a tau for a torque. These are rotational analogs for all these things. Newton's second law, in its linear form, right, relates linear acceleration to straight line linear forces. We know that forces in rotation are called torques. We know those torques will cause alphas, right? If I apply a torque to this wheel, I've changed the motion of the wheel. It went from 0 and now it's not 0, so there had to be an alpha. Okay, the omega changed here by the application of my torque. And this torque can either cause it to have positive alpha or negative alpha. Okay? The question is, what about mass? Well, the answer is we use this thing called moment of inertia. The moment of inertia is that capital I right there. And it is mass in rotation. So let's just real quickly, let's review what mass is, right? Okay. The more massive an object, the easier or harder it is to push. It's harder, right? Mass tries to capture that relationship, right, between how hard it is to get something to accelerate and how much you have to push. The bigger the mass, the more force is required to get something to change its motion. It's related to Newton's first law. What the moment of inertia is exactly the same idea, but just put rotation in all of those sentences. The more moment of inertia something has, the harder it is to get to rotate. It's all about rotation. So this bicycle wheel, I don't know if you've noticed it yet, okay? But do you see the weights that we've put on the outer edges of this bicycle wheel? We have increased the moment of inertia of this bicycle wheel. We've made it so that it requires more torque to get it to rotate than if it were made, say, out of carbon fiber everywhere and were super lightweight. The more mass something has away from its axis of rotation, the more moment of inertia it's going to have. Something you can do at home to get a feel for this, okay? I highly recommend you do this. Grab a broomstick, okay? And if you can take the mop head or the broom head off, it's even better, but you don't have to worry about it. It can be on there, okay? But if you just take a stick, okay, you notice if I grab it right here in the center, I can turn this stick pretty easily, just right with my fingers, okay? Now, grab the one end of your stick. Now, how hard is it to turn the stick? I mean, I'm kind of faking it a little bit, but not really. My thumbs are weak, okay? Physics fingers. It's much harder to get this thing to rotate. You can actually just kind of feel it, right? Okay? You just wave it up and down like this, and you can feel that it takes more force to get it to rotate. If I grab it here in the center, right, it's much easier to get it. Did the mass of the object change? No. What changed? The axis of rotation, right? It's where I was rotating that caused a change in the moment of inertia. So moment of inertia captures, okay, this idea of mass at distance, only for reasons you really don't want to know because it involves calculus, ends up being mass times the distance squared. So where this mass is, where it's distributed, makes a huge difference. Because distance from axis of rotation squared, right? And so if we double the distance, right, that the mass is distributed, we're going to end up with 4 times the moment of inertia. It gets crazy. So for an object, like the mass of my tennis ball here, right? If I swing my tennis ball around on the end of this string, I can find the moment of inertia of this tennis ball. What is it going to be? It's going to be the mass of my tennis ball times the distance squared. Did the moment of inertia get bigger or smaller? Smaller? Why? Less distance, right? If I increase the distance, I get a bigger moment of inertia. So for a single object, a child on a merry-go-round, they're just a mass moving around in a circle, their moment of inertia is going to be mr squared. But what about the meter stick, right? The meter stick isn't just one mass, it's got like mass that's extending, right? We could think of it as a bunch of little masses all connected to each other, right? This one's got mr squared, this one's got mr squared, this one's mr, right? Okay, and the other way, all mr squared. We can keep cutting this meter stick into little tiny pieces of mass. And for those of you that are in calculus class, if you cut something up into a bunch of little pieces and then add all those pieces up together, what do you get? Or what are you doing? You're doing integrals. Trying to look for the terror in your eyes. Right? Okay? I'm writing sums because I'm not allowed to do calculus in this class. Right? Okay? But really, we can integrate over these shapes. And luckily, somebody's done all those integrals for us. Namely, the author of your book and everybody else on the internet. And we have a table. Okay? This is actually the table I'm going to put on the exam for you, so that you have this as a reference. You don't need to put this on your cheat sheet or anything like that. I will give you the moments of inertia for objects, okay, via this table, okay? But this table consists of most of the basic shapes that all objects can be made out of. So for example, if I wanted to find the moment of inertia of a bowling ball, which one of these things would you pick? Yeah, solid sphere. Not thin-walled hollow sphere. That's fancy words for, what is this thing? What's a thin-walled hollow sphere that gets tossed into a basket? A basketball, right? Or a soccer ball, right? What's the difference between a thin-walled hollow sphere and a solid sphere? It's where the mass is located, right? A bowling ball is solid or mostly solid throughout. There's no liquid in there, but they change the material on the inside. But we can consider it all solid all the way through, right? But a basketball is filled with air, okay, which compared to the rubber of the ball is more or less, insignificant, negligible, so you had to think about it, right? And so that would be a thin wall. Which of these is a bicycle tire? Probably the thin-walled hollow cylinder, right? Because that's where the rubber of the tire is, right? But the solid cylinder might be like a car tire. Or maybe the hollow cylinder where like the rubber of the tire is actually thick. You could use that one. Where was the meter stick being turned around its center? A, yeah, slender rod, axis through center. You see how it's giving me the equation for the moment of inertia. It's 1/12 the mass of the rod times its total length squared, and I'm done. I don't have to do anything else, right? But notice, if I do B, slender rod on an axis through one end, now what's the moment of inertia? It's 1/3, right? That's a bigger, 1/3 is bigger than 1/12, isn't it? Matter of fact, it's 4 times as big, which isn't surprising because I put the mass at twice the distance, right? So moment of inertia is affected by location of the axis. Notice all of these things have an axis that is specified, right? Through the center, all that kind of stuff.
Come on, Gene, we don't need to count the second radius like.
Yeah, okay. It's a good question. The cool question is, why is there 2 here and only 1 here? The answer is, this is, when we say thin, we mean it's like really small, and the difference between the inner and outer radius doesn't matter. Okay, it's like the mass is kind of squeezed out along that whole thing. You'll also notice that that one says mr squared also. Okay, so if I had 40 tennis balls all rotating around at a distance r, I could find the total moment of inertia by adding up all 40 tennis balls. It would just be the total mass of the tennis balls times the distance squared. So that seems pretty consistent. You can mix and match on these too. So, for example, the moment of inertia of a car's wheel. So the wheel is the rubber part, the tire, as well as the central hub, the metal that sits on. I could do the central hub as the solid cylinder and then add onto it this hollow cylinder one to find the total moment of inertia of that wheel.
For that one, would you still be including R1 for the hollow cylinder?
Yeah. Yeah, I would do the thickness of that rubber tire, right? Okay. Now, technically it's filled with air, so we could argue about that. But let's see. A lawnmower blade? I'd probably do that one. I mean, you might do that one if they gave you the dimensions, but it's probably more like this. A baseball bat would be this. What about a ceiling fan? How would you make a ceiling fan out of these shapes? So a ceiling fan has got like a central attachment point, right? The round part in the middle, right? Okay. And then it's got these blades that come off of it, right? Let's say there's 3. Okay. So I'd probably use F for the central hub. And then for the blades, I'd probably use B. Just model them as rods. If you wanted to get really technical, I suppose you could do the thin rectangular plate axis along one edge, but really we're just spinning these rods, right, around, and I could take all, find one of the rods, multiply by 3, and then add that, right? You can build up shapes using this table to find the total moments of inertia of object. And the reason I can do all that is because all of these things share a common axis. Axis through the center, all that kind of stuff. So the table's pretty powerful, and we're going to reference it quite a bit moving forward, right? When we need to figure out what's going on with an object and we need to know its moment of inertia, I'm going to be like, table. And what is the closest thing that I can use from the table, right, to model whatever the object happens to be. So I did capture that into the PDF here, so that will be on your in the notes. Okay, so let's finish up with doing or at least starting an example of how to use moment of inertia and Newton's second law in rotational terms. We've got a bunch of stuff that's going on. Okay, we've got angular accelerations, we've got radii and masses. Okay. And they want us to find a coefficient of kinetic friction. This is a force problem, right? Like we know this is like a chapter 4, Newton's law, but now it's in rotation, which means it's chapter 9. We've got to identify which toolbox we're working with. Coefficient of friction normally, right, would come out of a chapter 4 problem. Sometimes out of like a conservation of energy, but we haven't done conservation of energy yet. We'll do that on Thursday. So my overall sort of conceptual framework, okay, the big picture is that I'm going to be using Newton's second law in its rotational form to try and figure this problem out, okay? So that means that I need a diagram, I need a free body diagram, I need something, okay? And the central actor in this problem is the potter's wheel. It's the thing that's rotating, it's the thing that's going to experience friction, all that sort of stuff. What do we know? We know that a 70 Newton force, this is like a top-down view. I put a picture of a potter's wheel down there, right? Okay. But like a top-down view, and the potter like applies a 70 Newton force. So like the potter's wheel is doing something like this, right? And they come in with their wet rag and they just push, right, along the edge of the wheel to get it to come to a stop. Okay. Now, that force, which is a normal force, the perpendicular surface, is directed right towards the center. So does that force cause a torque? No, it can't. It's not perpendicular to that distance. So what is the force that's causing the torque? We know there has to be a force perpendicular to the rotation. What is causing it? What's the force? Listen. It's friction. Right? They're asking us to find a coefficient, aren't they? What kind of friction is it? Static or kinetic? It's kinetic. This is rubbing, right? The wheel's moving, my hand isn't, right? So there's relative motion. So there's kinetic friction there. I'm just going to pick a direction of rotation for this wheel. I'm just going to say arbitrarily that its angular speed is going counterclockwise. Okay? That means the friction is pointed which way? The wheel is rotating this way but slowing down. Which way does the friction have to be pointing? It's got to provide an opposite torque, doesn't it? So at this point, is the friction up or down? We need the torque. If I hold my pencil along the radius of that circle, how do I get negative torque? If rotation this way is positive, I've got to point it down. Right? You see that? I've got to rotate this thing down like that. So my friction acts this way. If I say I'm rotating counterclockwise to get an opposite torque, I need a clockwise torque. That friction would have to be pointed down. All right. Let's see where this gets us. We do need a direction for positive, and I've already implied it. Counterclockwise. So what I'm drawing there, I may not have explained that. I will draw like a rotation, like a loop, okay? And then I'll put a positive sign in it. That means counterclockwise. Sometimes I'll even just put CCW. But I can also do it this way, right? What would that mean? Clockwise. Sometimes. All right. So that's my three-body diagram more or less set right there. I don't see any other objects that are sort of interacting. Let's see where I get by applying this right here. So I'm going to have I times alpha. It's just like M times A. Right, MA, right, I alpha equals, and now concentrate. How many torques are there in this problem? There's just two? I see one. Two forces, but only one of them's causing a torque. Which one's causing the torque? Friction. So it's going to be torque due to friction. Okay. We can put a minus sign on it because it is negative, but you can also leave the signs out. We know, right? Coefficient of kinetic friction is not going to have a sign on it. Okay, we'll just leave it for now. I alpha. Okay, so now I write down what the torque is. Remember, a torque is a distance perpendicular to a force. The force we have is friction. The distance is what? The radius of the circle. And we also know that the friction is fun, so this gets me minus r times mu times a. Run! Everybody run! Oh. Secret embedded signals in physics. Run! But now can I find that coefficient? I know the normal force, I know the radius. I've got to find alpha and I've got to find I. What am I going to do for the moment of inertia? What does the potter's wheel look like? I would pick the solid cylinder. It's like a solid disc, right? Okay. So the moment of inertia I'm going to use is 1/2 mass of the wheel, radius of the wheel, right? My alpha. Now this is interesting. They gave me the alpha, didn't they? Negative 0.87 radians per second. So I'm good to go there. And now I've got all the pieces, and I'm out of time now, but you can solve for that mu. It turns out, by the way, to be 0.312, for those of you who have to know. The answer, woo, that's a lot, and I would posit that that's the hardest part of this unit. right, is coming to grips with what we did today. Tomorrow we've got Center of Mass, I'll teach you about and we'll do a lab on. Thursday we've got to do energy and momentum, both conserved quantities, so it's nice that they go together. And then we will have finished this unit and we will be into test mode for next week. A fantastic rest of the day, and I will see you tomorrow.